Welcome everybody to this product demonstration highlighting FEKO for electromagnetic compatibility. To start with, just a brief introduction to FEKO, which is Altair's flagship product for simulation of high-frequency electromagnetics. Typical applications include antenna design, placement, and EMC. We offer a broad range of different solver technologies, which have also been hybridized to offer best of both worlds solutions, which means we can solve a different scale of problems from very detailed antenna design all the way up to electrically large platforms. The solvers have also been integrated into a modern and user-friendly user interface. And finally, we offer dedicated solutions, which include, for example, cable modeling, antenna arrays, and antennas. So here you can see an overview of, let's say, typical FEKO applications, where today we would like to focus predominantly on the electromagnetic compatibility. So here you can see a breakdown of more specific applications where FEKO is used for EMC. And in the demonstrations today, we're going to look at two different cases. The first covering radiated emissions, and the second example looking at high-intensity radiated fields. So let's start then with our first scenario, which is going to be related to cable emissions for automotive examples. And here you can see the demonstration model we're going to be using. Before I switch over to show you the model in FEKO, just a breakdown of the three different cable configurations that we will be comparing. In the first case, we have a single harness that runs down the side of the vehicle. In the second case, we split the harness around about the center and run a second harness down the middle of the vehicle. And the third case is the same as the first case, where here we add some additional shielding. In all three scenarios, we introduce an excitation at the middle connector. This is responsible for our radiated emissions. So switching over to FEKO, you can see the model here. In the first step, we import the CAD geometry into FEKO, and then are able to define our cable paths, which you can see over here. These can be defined directly in FEKO or also imported as CAD geometry. Once we have defined our cable paths, we can then also add some information about the cable cross-section to build up the cable bundles. And here you can see in this case we're using two center conductors which are embedded in an insulated environment. In scenario number 3, we will also use some shielding. As I mentioned, FEKO offers different shielding formulations. In this case, we will use the braided clay formulation. Once the cable is modeled, we can then also add different terminations in the schematic view. So here you can see our cable and the cable connectors, as well as different RLC terminations that are used in this case. Once we've run our simulations, we can switch over to post-FEKO and look at the different simulation results. So the first results that we're comparing here are the induced currents that are appearing in the one of the cable termination loads. And here the trend is quite clear, where the first configuration of the cable induced currents are higher, and these are reduced for setup number 2, and finally slightly further reduced for setup 3 with the shield. However, if we switch over to our radiated emissions or near field outside the vehicle, what we see is the trend is a bit less clear. At some frequencies, some of the setup is better than others. However, what is interesting, lower frequency, say beneath 40 megahertz, the emissions are slowly increasing. This is largely due to the vehicle chassis, which is somewhat suppressing the emissions. And then, in this case, about 40 megahertz, we see that the emissions are now radiating through, for example, the windows and the windscreens of the vehicle. Finally, FEKO also offers the possibility to perform time analysis, and the approach that we have here is to do this as a post-processing step, which has the advantage of being able to compare different excitation signals without having to rerun the simulation. So what we're showing here firstly is a digital signal pulse on our excitation cable. We have some rise time and some decay time. And if we then use this to calculate our radiated emissions, we can see then our E field time domain. This brings us then to our second example, where we're going to look at high intensity radiated fields for aerospace. Here you can see the overview of the benchmark model that we were using. What was interesting here is the frequency range covered a very broad band from 100 kilohertz up to gigahertz. And at 1 gigahertz, the platform is electrically fairly large, around about 50 lambda. And here you can see the incident plane wave excitation that was defined for the benchmark. We needed to calculate the near field at 4 points, 2 of which were inside the airplane and 2 outside. So outside here and here, inside here and here. And additionally, we also need to calculate the currents induced along the cable harness. So the approach we followed here was to use basically split up the frequency band into 5 different ranges. This also allowed us to use different mesh sizes and also to choose different solvers. So for example, under 100 megahertz with moments is most efficient for this problem, whereas above that we can switch to analog to solve the problem. So switching now to FEKO, here you can see the simulation model. So firstly, the model has quite nice detail, which we can see inside the fuselage. For example, we have some information about the different seating configurations, also in the cockpit, as well as some control panels, and finally then also the cable harness geometry. And here you can see the port where we calculate the induced current. This model is from the highest frequency band. For example, if we look at the meshing info, we'll see that the average triangle size is around about 3 centimeters, and that we have about 370,000 triangles in mesh. Also view that here quickly. You can see that the mesh that we use for the simulation. Once we've run our simulations and combined the 5 frequency band data, we can then plot, for example, firstly the E field points that were calculated. And here we can see firstly the 2 points outside the aircraft, where the fields are obviously much higher in the lower frequency range. And then the 2 points inside, similarly to before, we see an increase as the coupling is increased to the fuselage, and then above some frequency we have, let's say, somewhat similar behavior here. Finally, then we can also look at the induced currents on the cable harness. Here also some interesting behavior where, firstly, at the lower frequency we have a very constant current amplitude, and then as the frequency increases, we see some resonance behavior, also related to some standing waves that appear in the cable harness.